So it's quite late at night, and what better way to spend your late night video viewing pleasure than watching me make a selectable dummy load. So dummy loads are used for loading down the output of an amplifier, or indeed any device that's expecting some kind of load, instead of using the load that is designed to work with that amplifier. So for instance, if you're using a stereo audio amplifier for hi-fi or something, then instead of connecting a loudspeaker to it, you can connect a dummy load to it, which will present to the amplifier the equivalent electrical characteristics, such that the amplifier will happily drive away all its power into the dummy load instead of driving it into a speaker. So that's quite useful for testing, which is what you would usually use a dummy load for. So if you need to measure the output of an amplifier, you can't just stick your multimeter probes across it because, well, the amplifier's not loaded down. It's not doing any real work. You can't measure how it's performing when it's working if it's not working. And let's say you want to soak test an amplifier and you want to have it running for 5 hours at a given level producing noise. That would be pretty annoying if you had a full workshop full of them all making a lot of noise. So dummy loads come into play. I say it's going to be a selectable dummy load because we're going to be able to select the resistance that the load presents to the amplifier. So if you don't know, without going too far into various theory things, loudspeakers present an impedance to the amplifier, and impedance is like AC resistance. It changes per frequency, but we're not going to worry about that too much. A sort of standard impedance for a loudspeaker driver is 8 ohms, and for that reason I've got some 8 ohm resistors. Resistance and impedance aren't exactly the same thing, but theoretically an 8 ohm resistor should present almost identically to an 8 ohm loudspeaker driver. So instead of the amplifier making all of its power output and turning that all into sound and vibrating a speaker, when you connect a load like this to it, it's not going to make much noise, but it is going to get very hot because it's going to dump all that energy into heat instead of sound. For that reason, that's why these big power resistors are in a big metal case, and that's just purely to help dissipate the heat off of them. This is I believe this is a 25 watt resistor. So in theory, it can dissipate 25 watts. Although in practice, actually, if you look at the datasheet for it, it says that it can dissipate 9 watts. And if you strap it to a heatsink, then it will be able to dissipate the full 25. So by itself, 9 watts. I've got a project box here, which I'm going to build the dummy load into. It's made of die-cast aluminium, and I'll drill some holes in it, stick that somewhere inside, and that will additionally sink some more heat away. So if you were to leave this on for a long time connected, I guess it might get a little bit warm or something. Probably not too much. I wouldn't connect it to a big Marshall tube amplifier, but it's going to be all right if you connect it to a small hi-fi amp and maybe don't turn it up to full volume and leave it on that level. It's not going to do any harm. So I said it's going to be a selectable dummy load because in some instances it would be useful to have a different resistance presentable to the device under test. So for that reason, I've got another resistor here. So the lovely thing about the resistors is that there's one in alone, and it's 8 ohms, and if you were to connect that across, it would present 8 ohms to the device. If you connect two resistors in series, then we get 8 ohms, and we add another 8 ohms, so we get about 16 ohms. If you were to instead connect them in parallel across the device, resistors behave a little bit differently. You can sort of think about it as in the power going through them can get split two ways. And so each one of them, when you've got two, will present half the resistance. If you have three, they would present 1/3 the resistance, and so on. But because we've only got two, it's quite easy to work out. And because they're both the same value, it's quite easy to work out. We do 8 divided by 2. So we get 4 ohms if we connect them in parallel. In series, it's 16. And using those three combinations, 1 alone is 8, 2 in series is 16, 2 in parallel is 4. That gives us our normal range of impedances that a lot of amplifiers expect. Most amplifiers probably expect about 8 ohms. That's a kind of standard in the middle number. If you were connecting two speakers at once to the output, then maybe you would have a different impedance. And maybe some guitar amplifiers and other things would expect that. So we can demonstrate that. Let's grab a multimeter here. Let's get this out. Right, so they are 8 ohm resistors. So we're in the ohms range and we're on the lowest one. Let's turn it on. And yep, it's 0 ohms. Right, so let's connect this up. Connect it up. Yeah, we're just a smidge over 8 ohms. These are moderately expensive 1% tolerance resistors. So in theory, they should be plus or minus 1% from 8 ohms. And let's check the other one. Yeah, it's about 8.2. 8.2 is a standard value. 8 is not a standard value. So I suspect these might actually be 8.2. Even though they're labelled as being 8. If we bring in a little crocodile clip here, so they're both 8, we just saw that. If we link them together, we're starting to get into pretty basic resistor theory here, but it's useful to know if you've not done this sort of thing before. There we go, we link them together like that, and we get 16 and a bit, which is fine. If I squeeze the contact scope, it goes down a little bit more. It's not great contact between them. And if we keep those two linked together, and then let's try and connect both of them with this. So now we're going to try and connect them in parallel, you see. So we've got one connection on one end, the other end is tied together, and if I shove this on here, we get 4 ohms. Great. So there's the proof that it does in fact do that, if you needed proof anyway. And now let's take a little look at how we're going to get this into a box, and indeed what the sort of circuit is that we might need to do to make this. So in terms of a circuit diagram, it's not too difficult because we've only really got a couple of components. We've only got our 2 resistors, and we're going to need some kind of switch to switch between some kind of configuration of them. And the different configuration will give us our different resistances, which will present to the device that we're testing. So let's have a little look here. So if we have our 2 resistors, let's draw them in nice and big, and it's 8 ohms, 25 watts. Oh yes, all the power. 25 watts is not actually that much. You can get considerably larger power rated ones, but they do go up in price by quite a bit. So we're going to have some way of connecting an input to it, so we can connect our device under test on one side. What I'm going to do as well, because it'll be useful, I'm actually going to have 2 connections for either side of it. So I'm going to have 2 inputs and 2 outputs. They're just going to be directly parallel to each other. But what that means is that we can use one of the sets of inputs and outputs to connect to the output of our amplifier, and the other set of it we can connect to an oscilloscope or some other piece of testing equipment, I don't know, multimeter or something, and that will allow us to perform whatever measurement we need to do directly without having to sort of crimp onto or clamp onto wires that are dangling out of something or shoving multimeter probes into some other hole. So what I'm going to do is I'm going to have actually 2 inputs. That's not a very good arrow, but they're actually just going to be linked together. While I'm here, I may as well draw in a couple of outputs as well. And this is going to be the same thing. and they're just going to link together. Great. So we need some way of in one position, our switch will let us only go through one of the resistors. In another position, our switch needs to go through both of the resistors and then come out. And in a third position, we need to go through both resistors and come out of both resistors at the same time. I've actually got a 4-position switch, so there will be a fourth position where it's not connected to anything. I don't know. It seemed like it might be useful just to sort of almost have an off on it. Even though this dummy load isn't powered in any way, it can have an off. There we are. Easy. So we need to have 3 switch positions. So if we have a switch here, and we're going to be selecting between the 3 things. I'm not going to draw in the 4th off position. We're just going to have to remember that there is a 4th off position. So let's draw in our 3 contacts on that side of the switch. That's not a very good switch, but you get the idea. We're going to be connected to that one for the moment in this drawing. So we're going to come in here and we're going to go into both of those. Okay, so we are connected to the first resistor at the top, and when the switch is in this top position, let's say, we are also connected to that. So already we know that our 3-position switch, the topmost position here is going to be 4 ohms. So let's do the middle one as 8 ohms, and this one is 16 ohms. So when the switch is in the top position, we get a 4 ohm output, and when it's in the middle position, it's 8, and the bottom is 16. And how do I know that's going to be the 4 ohm one? Because only in the 4 ohm position do we have the input going to both of the resistors. Okay, so we need this one to come down and go to an output of some kind. But we need to be able to select, similarly, we need to be able to select in the 16 ohm position only. We need to come out of this resistor and go into this one. So let's draw in another switch here. And yeah, 4, 8, 16. Let's just give that a little numbering in there. 4, 8, and 16. No, let's keep the switches in the same position in all the places that they are. Good. So in the 16 ohm position, that would be when the switch is in the bottommost position. This connection would actually come around and down to there. Let's connect that on. Good. 16. Not that line. Good. And so then we have to have our 3rd position of making and breaking the circuit here. So when we come out of here, we've got our switch contacts again. Yeah. And let's keep it consistent. So this will be the 4 ohm position, 8 ohm position, and 16 ohm position. Cool. So in the 4 and 8 ohm position, we want to come out of this one, because in 8 ohm, we're just going through that one. In 4 ohm, we're going through both of them. In 16 ohm, we don't want to come out of there. We want to actually come out only of this one. So yes, that makes sense. So we come out of there like that, and the 4 ohm position as well, that links in. Yep, good. So in 4 ohm position, we're like that. And then in 16 ohm position, this comes down and links into there. Yeah, that makes sense. Does it make sense? Yes, it does. So, as it stands in the 4 ohm position, this switch is in the top position, so our signal can come in and go to both of them. It can't flow back round again because that's not connected to anything. This one comes down and goes out, and this one comes down and goes out. Yeah, so there's our 4 ohms in the 8 ohm position. It comes in, it can't go there because that would be in the middle and it's not connected. It goes up there, it can't go there because that's in the middle and not connected. It comes down there and it goes out. It doesn't matter that it flows backwards up into there because it's not going anywhere. And then in the 16 ohm position, the first switch is in the bottom position, so there's no connection. The second switch is up there, so our signal comes in, goes through this first one, comes along here. It can't go through the bottom because our 16 ohm switch is 16 ohm position in that switch is not connected, but it is connected here. So a signal comes in, goes through that one, along here, through the switch, down here. Can't go that way. It comes through this one, down there, and comes out. Good. So that's the basic circuit diagram. If you want to be correct about it, there's sort of lovely dotted ganging lines between the switches. But yeah, we get the idea. So that's the circuit diagram. We just sort of need to build it now. So in terms of the switch, you can't get easily a toggle switch, like a flicking switch that flicks to 3 or 4 different positions in a straight line, but you can get quite easily and cheaply rotary selection switches. So this is a rotary selection switch. There's a whole load of terminals on the bottom, and basically you just rotate it to the different positions. There's 1, 2, 3, 4 positions on this, hence why I've gone and given it a 4th position, which is off because the switches have 4 positions, so why not use them all? Great, so that's that. Let's move that out of the way and bring back our box, and let's grab let's grab a screwdriver. Let's open the box up. I like these boxes. You used to be able to buy them from Maplin, I think, at probably some extortionate price. And a lot of people used to make guitar effects pedals, like stomp pedals out of them. This one came from CPC. There we go. So there's our box opened up. In terms of the terminals I'm going to be using to connect to, so these connectors, I'm just going to use some banana plug terminals because they're nice and easy. They're on lots of test equipment, and it's quite easy to have. It's quite common, should I say, to have speaker outputs on an amplifier that are on banana terminals already, banana jacks, banana plugs, whatever you want to call them. So it'll be nice and easy to just get a short bit of speaker wire to link up to your amp and then straight into this device, and then come out of it on the other paralleled set of terminals to go into your oscilloscope or something. So let's see, we've got our resistors. I've sort of worked this out already, so hopefully it'll be pretty straightforward. But I think what I'm going to do is mount them on the sides, sort of like that. Hopefully the switch, it's difficult to do with no hands free. Yep, that's nice. Yep, all of you just fall over, that's great. Yeah, so the switch fits in between the resistors when they're mounted on the side, that's fine. I mean, I'm just shoving them in the box, but I'll obviously drill holes and it'll all go through. So they'll go on the sides like that. Let's do it from the top here. So we'll have the selector at the top somewhere. And then we'll also have our banana terminals, something like that. It might be that the resistors actually end up inside, sort of there-ish or something, but that's all right. Cool. So I think really the next step is probably to mark out and drill a bunch of holes in this. I won't bore everyone with doing that live in a video, so I'll be back after I've drilled a load of holes in a box. Right, so that's now nice and clean. All the holes have been drilled in it, so hopefully everything will fit. So let's have a little look here. We've got the one side of the contacts, and we've got the other side. Drilling not too difficult. Just needed to measure some things up, but otherwise fairly straightforward. There we go. They all seem to fit reasonably well. That one seems a little bit off, but it'll be fine. Let's ram those on there. I've also cut down the selection switch control rod, the actuator arm, the thing that you turn. I've cut that down because, well, it's now that long. I've got another one over here somewhere. Yeah, it was that long. I guess they must supply them for all kinds of different things, but that was a very long rod. So let's shove these on there. Certainly just enough to hold them in. It's always useful going on the data sheet for these things because they have all the sizes written on. So for instance, for the resistors, it was quite easy to work out. Without measuring that, I could just refer to the data sheet. It's always worth doing. Likewise, this little extra hole in here, which matches up on there. So there's a little stud on there. You can see that. Just to stop it rotating. I'll do those tighter in a moment. So yeah, you can see that little stud just fits into the hole there, and stops it rotating when you turn the switch around. So let's put that on. Actually, having now looked at it, I'm probably going to need to do that switch last, because to get to these, the holes for those on the side, especially the bottom ones, it's going to be quite difficult. So let's go and grab some of these bits. There seems to be a nut already out, so some nuts. 3, 4 of those. Sorry if you can hear underfoot. That's now all of the metal shavings that were cut off, all the chips. Let's see. Yeah, I'm going to have to undo the switch because it's going to be impossible to get it on. I'll come back in a minute once I've connected all of these things together, or at least attached them all to the box, because otherwise it's going to be quite tedious watching me screw them all in. Right, so we've now got all of the components fixed in. They're all screwed in or screwed down or however they're attached. Our switch is in, our resistors are in, they are heatsink compound into the edge. Naturally, of course, I don't know whether the tube had just been hot or something, but as soon as I opened it, it squirted out everywhere and covered me and the resistors in heatsink compound, so there's far too much in there. But yeah, let's just give a little close-up of all the insidey bits. You can see what's going on. Oh, that makes the exposure go a bit crazy if I do that, so I won't. There we are. And then our 4 positions, we've got 1, 2, 3, 4, and they will be our 4 positions. So I'll just quickly tidy this away and we'll just quickly solder all of this stuff together. So we're back again, and it's now time to wire this up. If we bring the wiring diagram back in, I've actually gone in and added a couple of things. So we've got A, B, C, and then you you can see 2, 3, 4, the 6, 7, 8, and 10, 11, 12, and they actually correspond. The pins on here are numbered and lettered in the center. So currently the switch is in its leftmost position, like the first position, and in that position you can see there's some little black dots I've put in there that mark off the 3 segments of the switch. So in the first position that we're in now, A, which is, let me just see, A is this one, this pin here. A is connected to pin 1, B is connected to pin 5, C is connected to pin 9, and then as you click it round, they go around the numbers. So if we go off this, then we can see our inputs. It doesn't really matter which of these are the inputs or the outputs. It's the same either way. I'm going to have it like that because it's easy and it stands up, so it's easy to solder. I'll put that there where I can see it. So we need to connect the inputs to A. Let's be consistent and use some black wire for this. And we also need to connect the 2 inputs together. So let's actually tell you what, I'm just going to get my wire strippers. Automatic wire strippers and some magnets apparently. Right, so let's just strip off a little bit of this. And then we're not going very far. I could go in here and put and cover it all with heat shrink tubing as well, but I don't think I'm going to bother, just because I'm pretty confident that most of it's going to be out of the way of any of these things. Let's also, while we're here, let's do this red one as well. So roughly the same length, about there-ish. Yeah. I quite like these automatic wire strippers. They're useful, especially if you're working on a big job. It's useful to be able to strip them quickly without thinking too hard about it. Good. So let's get some solder in here. It's always a little bit awkward when you've got to work inside something else, but it's not too bad in this instance. It's also a lot more tricky when you've got a camera in the way. Let's just tin these. Okay. Let's give these a quick tin as well. Come here. One. Two. Oh, that's not very good at all, is it? It's very hard to see what you're doing when there's a camera in the way. Let's just get that over there. Good. So then we need to hop over to this one, and we'll get some more black wire. And this is going to hop over to terminal A on our switch. So we're going to go about that long. I probably said multiple times this is going to be quick, but it's clearly not going to be quick in any way. I mean, it's probably quicker than waiting for one to arrive in the post if you were to buy one, I guess, but certainly not an instantaneous build. And of course, you've got to have all the parts on hand and all the rest of it. It's actually quite long, the amount that I've got exposed here. So I'll tin the other end as well. This is actually already pre-tinned wire, but that's fine. So I think what we'll do is to try and keep it somewhat consistent with our diagram. If we have, so there's A in the middle here. If I use the Y to point to it, that one there is A. So this one will be our contact number 2, which will go to a resistor. So I think actually what we might do is bring that one round to this end here of this resistor, and then this end can be an output. It'd be a bit neater if we can do it like that. Right, I think I'm going to need to get in here nice and close so I can see what I'm doing and I don't make a mess of it. So I will join you again when it's all done. And just like that, the magic of video, we are done. That was really quite annoying to do. Just because of the angle of the box. It's a bit difficult to see when you're straight up and down on it, but there's quite a lot of angle to get down in there. And obviously these ones are quite close to the resistors and so on. And so it's just a little bit tricky to get some of them. And obviously then the resistors themselves, big heat sinks, and yeah, a little bit tricky to make sure everything flowed nicely. Certainly not the best job I've ever done on any kind of soldering, but it's definitely functional. Let's put it that way. So let's put the back on. In fact, let's just quickly move away all of this wire and stuff, so we've got some space. Shove all this out of the way. There we go. So there we are. Yeah. All I did was use the black wire to go and make it a little bit more visual here. So the black wire is essentially this side of things. You can see it's jumping between the two. It goes up to our A point, and it also goes up to the input of one of the resistors. The yellow wire is showing this sort of cabling up in here. So we've got a cable coming off of the switches, and B and C are linked together and link up to the end of this resistor. Red is then everything down here. So these terminals here, the output terminals, so to call them, and the output of this resistor. I mean, there is no in and out. You can connect it either way. It's just nice to have some color consistency. I also realized when I was mounting everything that this bottom piece doesn't quite go on, just not quite, doesn't quite fit. These resistors were just slightly too high, and they should have gone a little bit lower than they did. Not a problem though. I've just had to file some notches out of this, and now it fits on there perfectly. So let's pop these screws back in. If I can find where I put the screwdriver. It's there. Yeah, so it's quite a sort of relaxing little project to do. It's probably taken me, it's taken a couple of hours from laying out the components to having it finished. Something you can do quickly in an afternoon, or in my case, overnight. Of course, I'm doing the famous thing of putting it together before I'm testing it. Right, so in theoretically we've got our 4 positions, and so let's grab some banana terminals. Yeah, I guess it doesn't matter which one's going where. In as much as it doesn't matter, I can do this if I want to. They're still going to read the same. And somewhere, let's just grab the multimeter back in again, and this mess of cabling here. Let's just sort all this out. They've obviously got tangled. Oh God, there we go. Right, so we are in ohms mode still. Let's shove that one on there. And shove this one on this side. They weren't the most expensive banana plugs, and that feels quite loose in there. I'm not sure what's loose. It might well be the actual banana cable itself. Who knows? Good. So we're reading nothing at the moment, which is good because we're in the off position. So to call it, I mean, off. Just no connection between the 2 terminals at the moment. So hopefully when we click this round, we should see, what was it, 4.2 on there. Well, yeah, it's close enough. There's all this cabling and connections, and that's, yeah, it's obviously a bit of a loose connection in some of this dangling stuff there, but there's our 4. There's our 8. And our 16. So there we go. There is our, that's the wrong screwdriver for that. There is our selectable dummy load. So that's been quite successful, really. That's all gone together. Just pop the little cap on there. That's a sure sign of being done, isn't it? Finishing off all the screws. Let's just, for sake of argument, show that they are crossed over, and it doesn't matter which way around they go. Yeah. I'm reading quite high, but then that's, as I said, this lead isn't great. Yeah, there's our 4. 4. 4. Good. So that's showing that all of that works. We are done. Project complete. So there we go. From thinking about it to drawing it up to finished product in a couple of hours, there is our selectable 4, 8 and 16 ohm dummy load.